compound probability. Basically what we're doing today is you're calculating more than one probability. Now, thinking about our quiz yesterday, remember, we've basically covered two big concepts: fundamental counting principle and probability. Fundamental counting principle is where you multiply the outcomes together. So if I want to make some different outfits out of 5 tops, 4 pants, and 2 pairs of shoes, I multiply 5 times 4 times 2, and that gives you the outcome. Probability is when you have the fractions are and dividing those. I had some people kind of mixing those two things up. Probability is where you're calculating the percent chance. Now, compound probability, it sounds fancy. It's just more than one. We're going to have 2 fractions today, people. So it's the probability of 2 or more events. Come on, board. Okay, so you could have, we've talked about these individually, but just to kind of give you an example here, you could have, of course, let's say, I don't know, tossing a coin. Now, we're going to see tossing a coin today. How many outcomes are there for tossing a coin? 2, heads or tails, right? I'm going to put and. So here's where your second fraction would come from. Maybe we're going to talk about rolling a die. Now, rolling a die, I actually had a kid come up 8th hour and ask me during the quiz, ask me what a die is. I was like, that's singular of dice, right? Singular, it's just one die, okay? So of course you have 1, 2, 3, 4, 5, 6. Now this looks fancy, but it's just kind of wordy. We're going to talk about it. It's the math that matters involved here. So independent events. The outcome of one event does not affect the other one occurring. So tossing a coin has no bearing on rolling a die. Those are completely separate events. They are not related. We will talk about if they're related on the backside. So basically, we're going to talk about independent events. When A and B are independent. So the probability, super easy. You just do the probability of your first event. So remember, that's going to be a fraction. Now, I'm going to try to put a big for dramatic emphasis. You're multiplying by the probability of the second event. So if you have multiple events today, so 2 fractions, we are multiplying them together. That is the exciting math that we are going to be doing. So here you can take a look. We've got on the first 2 there, use your spinner, of course. The spinner to the left is spun. Letter from the word bingo is chosen. So I'm going to start with the spinner. So first, easy question. You know I like to always do the total first. How many total numbers are there to land on the spinner? 10. Now, we're just going to count the favorable outcomes. How many of those numbers are less than 7? 6, because does 7 count? No, I had some people counting that in situations like that. You know that doesn't count, so I'm going to leave it 6. Okay, then we've got this word bingo here. They're talking about you pick a B out of the word bingo. Well, how many total letters are in the word bingo? 5. And how many B's are there? Okay, exciting math here. So there's my 2 probability fractions. Those are independent events. We multiply the answers together. Now you can do that all in your calculator, of course. Multiply fractions, easy peasy. Just do the top. 6 times 1, 10 times 5. And I'm just going to reduce that down to 3/25. And remember, unless it specifies, you can give me a fraction, you can give me a decimal, you could give me a percentage, whatever it wants. Okay, so same thing. So 2 are still on the spinner. So we know there's 10 numbers on the spinner. Now, at least 3. What does that really mean? Any number more than 3. Does that include 3? Yes. So 3 and above. So 1, 2, 3, 4, 5, 6, 7, 8. There's 8 favorable outcomes. All right, now I'm going to do my word bingo. We said there's 5 letters in the word bingo. Do we know what our vowels are? I hope, right? What are the vowels? Perfect. Okay, so vowel. How many vowels are in the word bingo? 2. All right, we're going to multiply. So we're going to have 16 on the top, 50 on the bottom. And of course, I just reduced it down 8 over 25. So I kind of like today because it's really not anything new. It's just you have multiple fractions to calculate per problem. All right, 3, we're not looking at the spinner anymore. The spinner was only for 1 and 2. A die is rolled 2 times. We just talked about this. How many different numbers, how many total outcomes are there on a die? 6. Now, it says we're rolling the die 2 times. So I know there's 6 for each roll here. What's the probability of getting a number greater than 4 on both rolls? So let me ask you a question. Does 4 count? No. So your only 2 favorable outcomes are what 2 numbers? 5 and 6. So we have 2 numbers per roll. We're going to multiply it. So you have 4 over 36. And you can always reduce on your calculator. 1 over 9. Okay. Oh boy. A number from 1 through 20, that's a lot of numbers, guys, is chosen at random. So let's do this number part first. Now, 1 through 20, 20 numbers. Okay, I'm going to do the coin in a minute. Prime number. Now, we've seen prime numbers a lot here. I'm going to list them on the bottom, 1 through 20. I'm going to start with 1. Is 1 prime? No, 1's not considered prime because it's just a single number. Is 2 prime? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so count them. 8. So we have 8 favorable outcomes. So that's just kind of tedious because you have so many numbers there, I'm aware. Okay, now we're going to do the coin. So your coin is flipped. Well, you just told me you have 2 possible outcomes, heads or tails. So I'm going to put that down. Okay, what's your probability of getting a tails? 1, yeah. Okay, so multiply, we're going to have 8 over 40, which I'm going to reduce to 1 over 5. All right, any questions I can answer for you on that? Deck of cards, my friends. Here we go. Now, we know this. It doesn't say, but I know you know it. How many total cards are in a deck? 52. Good, okay. So cards chosen at random from the deck of cards, replaced and another one's chosen. What's the probability of a diamond both times? Well, you just told me there's 52 cards in the deck. So my next question is, how many diamonds are in the deck?
16.
I hear 4, I hear 8, I hear 16. There are 13. A quarter of the deck is diamonds. And remember, you're doing that both times. So it's the same fraction. Now, of course, I'm not going to bore you with all the math. You can punch it in, reduce it. Your final answer, 1 out of 16. Okay, the month of the year and day of the week is chosen. Let's start with the month of the year. How many total months are in the year? 12. Now, choosing a month starting with J. How many months start with J? Okay, what are the months? January, June, July. Okay, then we're going to talk about this day of the week thing. Now, easy question. How many days of the week are there? 7. And how many of them are Wednesday? 1. All right, so we get 3 on the top, 84 on the bottom. Doesn't simplify. I'm just going to circle it. I like it. Okay, coin is tossed 4 times. What's the probability of getting heads each time? Now, you've told me already there's 2 outcomes on a coin. How many heads are there? 1. And it says we're doing this 4 times. So we have 4 of these 1 out of 2 fractions. So of course multiplying the top's easy. 1 times 1 times 1 times 1. 1. What's 2 times 2 times 2 times 2? 16. So that's 1 over 16. All right, Vera guessed on the last 3 questions of a multiple test. I'm just going to scroll this up because I feel like it's about What is the probability she got them all correct? Okay, so she guessed on the last 3 questions. That makes me depressed, but whatever. If each question had 4 answer choices. So we have 4 total outcomes. Well, what's your favorable outcomes? She got all of them correct. 1. There's only 1 shot that she got all 4 of those correct. Now, we're talking, though, she answered, how many of these did we guess on? So we have 3 of these guys. So 1 times 1 times 1. I'll do the top. That's easy. What's 4 times 4 times 4? 64. Now, sometimes I like to think about these as percentages. I mean, because think about this. If you're guessing on questions on a test, is the probability you're getting them right kind of low? I feel like if you do the percent on that, which I did the percent, it's 1.6%. I was like, yeah, that tracks. It's kind of low. Yeah, it's kind of low. All right, there are 14 girls and 11 boys in Mr. Haynes' homeroom. Do some math there for me. How many total kids is that? 25. Okay. 9 girls, 15 boys in Mr. Jump's homeroom. If a student's chosen at random from each class, what's the probability they are both boys? Okay, you just told me 25 for the total. Now we're doing the probability they're both boys. So how many total boys are there here? Our favorable outcomes. Now we do have a fun little thing to talk about. Now, if we're talking about Mr. Haynes, okay, there's total of 25 boys, and now we're talking about Mr. Jump. Here's a question for you, easy question. How many boys are there in Mr. Jump's home? They're down to 24, because we already picked one there. And what's the favorable outcome in Mr. Jump's homeroom? 15. Because there's both, we took a boy out of the total because we're doing the same thing. Okay, you can multiply it, simplify it, all the things. You end up with 11 over 40. All right, final one of these guys. Why are we guessing on these things? Okay, Christian is guessing the 4-digit code to his parents' garage door. Sounds a little sus if you ask me. What's probability each digit is greater than 5? Well, okay, 4-digit code. So I already know I'm going to have 4 fractions here. So I'm just going to set them up. Now, let's first talk about our total outcomes. How many total digits are there to pick from? We've seen this before, 0 through 9. How many numbers are 0 through 9? 10. And just if you're like, where did we get that? 0 through 9. Okay, so I'm going to put 10 for all the bottoms. What is the probability each digit's greater than 5? So what are your favorable outcomes? 6, 7, 8, 9. So how many? 4. And each fraction is going to be the same. Okay, so multiply it, reduce it, all the stuff, you end up with 16 over 625. Got it. Any questions on that? Okay, and one last easy thing to show you. We're still multiplying fractions, but now we're going to talk about what we consider dependent events, okay? Now, don't be like, oh gosh, how am I going to remember what's independent, what's dependent? It's going to be very obvious and easy. The key you have to remember today is you are multiplying the fractions together. So events are dependent. If one outcome of an event does affect the outcome of the second event, you're going to see some examples down below. So with multiplication on this, it's still multiplying. You're going to do the probability of your first event times, still multiplying, the probability of the second event, but you have to consider after the first one. Now you're like, what in the world is all of that about? I'm going to click it back a slide because we actually kind of snuck one in on you. 9. 9 is kind of an example of dependent events because the fact they're both boys, didn't that affect my total on the second fraction? I had to knock it down to 24. That's what we're going to do on these last few problems. Those are dependent events. I didn't like come up with some crazy formula or anything. I just thought about it. Okay, so marbles. We know marbles here. Well, let's first total them. You've got 3 blue, 10 green, 4 yellow, 8 red. How many total marbles are there? So let's start with 25 total. And notice red. Let's do the red fraction first. Now, How many, read it, how many red marbles are there? 8. We're multiplying. Now, key phrase here. Marble drawn at random, not replaced. So I drew a marble out of the bag. How many are left for me to pick from now? 24. Because I didn't put that original one back in. Okay, just read it. How many of them are blue? 3. Okay, so you can multiply, do all the stuff. You end up with 1 out of 25. Okay, so same type of thing. I'm going to start with the green. There's 25, of course. How many total green ones are in the bag to pick from? 10. I know the yellow doesn't show up great, but let's do it. No, we didn't replace that, so you're down to 24. How many yellow marbles are there to pick from? 4. All right, you do all the math, multiply it, reduce it. You end up with 1 out of 15. Okay, both red. All right, so we already did the probability of red, but I didn't replace it. So how many total are there to pick from? And remember, I pulled out red, I didn't replace it. How many on the second draw are left to pick from for red? 7. Multiply it, reduce it, you end up with 7 over 75. Over 75, got it. Okay, both yellow. All right, well, we can do that. We know there's 4 yellow, and there's 25 total. Now again, I drew a yellow out, I didn't replace it. What is your fraction for the second probability of yellow? Perfect. And again, multiply, reduce, blah, blah, blah. You end up with 1 out of 50. So I kind of like this stuff, not too shabby, my friends. Okay, last one. And we can make a Venn diagram if we think it might help us. We'll just see what we think here, because this is kind of wordy just for the record. Okay, let's see what we got. Let's not do yellow. I know it doesn't show up the best. Very wordy. After the completion of a race, 75 runners, that's important, 75 runners, were asked if they ran a personal best time and if they trained for the race. Of those surveyed, 22 said they had a personal best time, 46 said they trained for the race. Of those that said they had a personal best time, this is getting wordy, 18 had trained for the race. If 2 runners in this group are chosen at random, find the probability. So first one, both runners trained for the race, but did not run a personal best. Well, I know it's out of 75. Now, if you're like, oh gosh, how am I supposed to figure out how many trained that didn't run a personal best? Like I said, we could, I'm just going to do it on the side. You have room on the left side, I have room on the right side. So we could think about we had a personal best and we trained. So I'm going to try to interpret these numbers so I can figure out my favorable outcomes. So one of the things, of course, it tells us on this, it says of those that had a personal best, 18 trained. So I know I've got 18 in the overlap. Okay, I like that, that helps. Now, it also says of those surveyed, 22 had a personal best. Well, if I already have 18 in the personal best, how many is left for the personal best circle? Well, there's 22. Okay, trained. We got to read the trained part here. And 46 said they trained. Well, you have 18 already in the trained circle. Total of 46, 28. So I'm hoping this will kind of help us here. So both runners trained for the race, but did not run a personal best. So how many trained, but no PB? 28. So I kind of had to do all that to figure out the 28. Which some of you maybe could have read it and figured it out. Now it's easy. Now it's easy. Both runners. So we already did the first runner. It's the same probability, but we already did the first runner. So we're down to 74. And what's your numerator down to? 27. All right, I multiplied it, reduced it. Man, this is a bad fraction, guys. 126 over 925. Ooh. Right. Okay, so same little Venn diagram. We know we're over 75. to start with. Let's read it. One runner had a personal best time. All right, well, let's do that guy. How many total are in the personal best circle? The whole circle. 22, 4 and 18. And, okay, so now I'm down to 74. I gotta read it here. And the other runner neither trained nor had a personal best. So we gotta do some math. I like the 25 because we're not in these circles, but there's 75 total. So to get the total of 75, there's 25 that didn't do anything. Lazy. Okay, multiply it, reduce it, all the things. You get 11 over 111. So that to me is the trickiest one because it is so wordy, okay? So let's do this.